Welcome back to Mandaka, where we unravel the universe's most mind-bending mysteries. Today, we're diving into something truly incredible: the idea that time itself isn't constant. In fact, clocks in your basement actually tick slower than those on your roof. That's right. It sounds like science fiction, but it's a fundamental reality of our universe, predicted by Albert Einstein over a century ago. It's called gravitational time dilation. Gravitational time dilation, that's a mouthful. So, you're telling me that if I put two identical clocks, one in my basement and one up on my chimney, the basement one would eventually fall behind? Exactly. Though I must emphasize, the difference would be incredibly tiny, imperceptible to us without highly specialized equipment. But yes, the basement clock, being closer to the Earth's massive core, experiences a slightly stronger gravitational pull, and that affects how time flows. How can gravity affect time? I thought gravity was just about things falling down. That's a great question, and it gets to the heart of Einstein's general theory of relativity. Einstein showed us that gravity isn't just a force, it's a curvature in the very fabric of spacetime itself. Spacetime fabric? Like a cosmic trampoline? Precisely. Imagine a bowling ball placed on a stretched rubber sheet. It creates a dip, right? That dip is what we perceive as gravity. Now, in this analogy, the sheet isn't just space, it also includes time. So, massive objects like Earth create a dent in space-time, and that dent slows down time itself? In essence, yes. The deeper you are in that gravitational well, the more space-time is warped, and the slower time ticks relative to someone in a shallower part of the well, or someone far away. That's mind-boggling. But if the effect is so tiny in a house, how do we even know this is real? That's where atomic clocks come in. These are the most accurate timekeepers ever invented, so precise they can measure differences down to billionths of a second. Scientists have conducted numerous experiments over the decades. Tell me about one of those experiments. One famous one was the Haffel-Keating experiment in the 1970s. They flew atomic clocks around the world on commercial airliners and then compared them to stationary atomic clocks back on Earth. And what did they find? They found that the clocks on the planes, which were experiencing both velocity time dilation due to their speed and gravitational time dilation due to their altitude, indeed showed minuscule but measurable differences compared to the ground clocks. The results perfectly matched Einstein's predictions. So, it's not just a theoretical concept, it's been experimentally proven. But does it have any practical applications, or is it just for scientists? Oh, it absolutely has practical applications. The most significant one you use every day is the Global Positioning System, or GPS. GPS? My phone's navigation system relies on warp time? It absolutely does. GPS satellites orbit Earth at about 20,000 kilometers up. At that altitude, they experience significantly less of Earth's gravitational pull than we do on the surface. Less gravity means time ticks faster for them, right? Spot on. The atomic clocks on board the GPS satellites tick about 45 microseconds faster per day than clocks on Earth. That's a huge difference when you're talking about precise positioning. 45 microseconds a day doesn't sound like much, but for GPS, that must add up quickly. It does. If engineers didn't account for this gravitational time dilation, and also a smaller effect from velocity time dilation, the GPS system would accumulate errors of about 10 kilometers per day. Your navigation would be completely useless within minutes. Wow, so what seems like a subtle cosmic quirk actually underpins our modern technology. It's incredible to think about. It really is. It demonstrates how deeply our universe is intertwined with these fundamental principles. From navigating your car to sending probes to other planets, understanding how gravity affects time is crucial. You mentioned black holes earlier. I can only imagine how extreme time dilation gets there. Near a black hole, the gravitational forces are so immense that spacetime is warped to an extreme degree. If you were to approach a black hole's event horizon, time for you would slow down dramatically. Like in the movie, Interstellar. Exactly. Interstellar did a fantastic job of visualizing this. An hour spent on a planet orbiting near a black hole in that movie equated to decades passing back on Earth. For an outside observer, someone falling into a black hole would appear to slow down and freeze at the event horizon, never actually crossing. That's truly mind-bending. So, time isn't a universal, constant flow for everyone. It's relative to your position and speed. That's the takeaway from Einstein's theories. Time is not an absolute, fixed entity. It's flexible, and its passage is influenced by gravity and relative motion. It means there's no single, universal now, for everyone in the cosmos. This makes me look at my watch differently. It's not just counting seconds, it's counting my seconds, influenced by Earth's gravity. It makes you feel very connected to the universe's fundamental laws. It truly does. The clock in your basement ticking slower is a tiny, everyday testament to the grand, relativistic dance of mass, energy, space, and time that governs our entire universe. It's a beautiful, intricate reality. Absolutely fascinating. Thank you so much for shedding light on this incredible topic. My mind is officially blown. My pleasure. It's a concept that never ceases to amaze.